Have you ever wondered why we use steel bars inside concrete? Can concrete withstand loading without these steel bars? In this lecture, you will learn the design principles behind using these steel bars in reinforced concrete beams. Welcome back, everyone. If you have been following along, you now have a solid foundation in the basics of reinforced concrete, its applications, and the materials involved. If you have missed any of those, be sure to click here to follow along. In today's lecture, we are exploring the design of singly reinforced concrete beams. We will explore the theory behind it, breaking down the principles that make these beams strong and efficient. So grab your notebooks and let's get started on part 4 of Reinforced Concrete Design Series. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. This channel is about civil engineering and human skills to help us lead more productive, happy, and examine life. How do we design singly reinforced beams? By singly reinforced beams, we mean that reinforcement is provided at the bottom of the beam. The first thing is initial sizing. Now these are rule of thumb. Now these rule of thumb are very important, especially when you do not have any standard sections. Now the sizing is really controlled in reinforced concrete by the architectural requirements most of the time. We have these rules of thumb. First one is for simply supported beam. The span to depth ratio is 14. So for example, if you have a span of 5 meters, okay, this is span to depth ratio. So span to depth is equal to 14. So from here you can work out the depth. 5000 divided by 14, it will give you 357. So from here you can work out the depth of the beam, and then you can say that okay, the depth has to be slightly higher. You could say that okay, this is, you're assuming it to be 400 millimeter, and the width of the beam should be greater than 1000 V over 2D. V is the maximum shear force. So for example, if shear force is say 50 kilonewton, shear force will depend on your shear force diagram. So for example, if shear force is 50 and then divided by 2 times D, depth we have taken as 400, so this will give you 1000 times 50 divided by 800. So this is giving really very small 62.5 millimeters. So you can assume it to be say 100 or 150 millimeter. All right, so these are rule of thumb. I mean, these are not the design code requirement, so you can always have something greater than what comes out to be from rule of thumb. They will get you started when you don't have the size of the section, but here in this module, I mean, certainly we will have sizes all the time, but this can be really very useful when you are working in industry. For slabs, you have one way spanning slab is a different one, and then again interior beam and other beams, cantilever, you have different span to depth ratios. Now again, this is a cross-sectional area of the bars. So for example, if you're using 20 millimeter bar, and then if you had 2 of them, then this table will directly give you the area. The area, this is simply area of a circle. So area of a circle is pi by 4 d square. For example, for 20, it would be pi by 4 into 20 square. It will roughly be this value, pi divided by 4 into 20 square, 314. So here you can see that you have this 314. And then again, if you multiply it with 2, you get this. So in this table, you don't have to work out area again and again. This is simply area of a circle because bars are circular. Now, concrete strength, there are different strengths. The most common ones are C30, and its Young's modulus is given here. Its tensile strength is given. We will not need tensile strength. The design compressive strength of concrete is 0.85 times FCK divided by gamma C, where gamma C is 1.5. When you put these values, you will get FCD as 0.567 FCK. So keep this thing in mind and then FYD. Now remember that in the stress diagram we had these values, and FYD is FYK over gamma S, and gamma S is 1.15. So 1 divided by 1.15 will give you 0.87. Okay, so gamma S is 1.15. So that's why if you put this value, you will get FYD as 0.87 FYK. Now keep two things in mind. FCD is 0.567 FCK. FYD is 0.87 FYK. FYK is the yield strength of the bar. Now concrete is brittle. It is assumed to fail at ultimate strain of 0.0035 or 0.35%. The design strength of rebar is 0.87 FYK. Now it's often necessary to see if the bar yields before concrete has failed in crushing. So the yield strength is worked out from here. So yield strain is equal to FYK into gamma S into, this is actually coming from Hooke's law. Hooke's law is F is equal to epsilon E, where epsilon is a strain, F is a stress, and E is Young's modulus. Now here we are using this safety factor for the bar. So that's why we have FYK 500 divided by safety factor is 1.15 and divided by the yield strength of steel, which is common 210,000, which we've been using in the structural steel as well. So this is giving us yield strain as 0.002. So yield strain is 0.002 for steel, and yield strain for ultimate failure is 0.0035 for concrete. What is our purpose here? What we are trying to do here? You know how to work out the applied moments. If you have a uniformly distributed load, if you have a point load, then you can work out its MED or applied load. Now here we are trying to work out the moment capacity or MRD, moment capacity of the beam. So how do we work out moment capacity of concrete beams? In case of steel beams, we said it is WPL-FY over gamma M0. But here it's not that simple. So we have to derive that equation and then we will use it in a formula. As our case is singly reinforced beam, here we are not considering these top bars A-S. Then you can see that this is cover, and the bottom circles that you see here, 4 of them, this is your tensile reinforcement. The depth of the section is always counted from the middle of tensile bar. So the middle of tensile bar to the top of the beam, that is your depth. And your overall depth or height of the section is always from the bottom to the top. But depth, when we talk about depth of the beam, it is always from center of the tensile reinforcement to the top bar. Now you can see here that this is called cover, and then we have stirrup. Inside that stirrup we have these AS or main tensile reinforcement. At the top you have compressive reinforcement, but we are not talking about compressive reinforcement for the time being. And from the center of compressive reinforcement to the top we have this D dash, and these links, these are termed as shear links or stirrups. Let me draw the stress diagram. Now you can see that the tensile stresses are taken by tensile force, which is at the bottom, and the compressive stresses are taken by compressive force in concrete and compressive steel in concrete. But we are not talking about compressive steel for the time being. So we are simply talking about the compressive force in concrete. From the bottom of this stress block to the top, it's 0.8 times x, and x is the distance from neutral axis to the top. So tensile force in rebar is equal to area times stress. So force is always equal to, any force is equal to area times stress. This is a famous formula. Or stress is equal to force over area. So if I use this logic, then the force in tension is going to be FYD, which is the yield strength, times area of steel, where FYD you saw earlier, FYD is equal to 0.87 FYK. And the reason is that FYD is design yield strength. Design yield strength is equal to FYK over gamma S, where gamma S is equal to 1.15. I explained this little earlier. So if I put this 0.87 FYK in this equation, it will give me the tensile load as 0.87 fyk into AS, where AS is the cross-sectional area of tension steel. Is it clear up to this point?
Yes.
Excellent. Now in the same way, we have to find out the compressive force. Now compressive force will be again equal to stress times area. Compressive force C or CC in this case is equal to FCD times AC. A is the area of concrete. FCD, on the other hand, we found out little earlier that FCD was equal to 0.85 FCK divided by gamma C, where gamma C was 1.5. So if you put these values here, you will get 0.567. Remember that FCD is design concrete strength. The reason for using design is that obviously we want to go for the safest option. The stress times area, stress is 0.567 FCK, which is from here, and area of concrete. Previously, area of steel was simply pi by 4 d squares. Now, area of concrete will be area of this concrete block. So it will be B, that is width of the beam, times the depth of the block. The depth of the block is 0.86. So width times depth will give area of the concrete stressed block. So this is something which is being stressed. So that's why it is B times 0.8x. And FCD is equal to 0.567 FCK, which I already explained. And D is the effective depth or depth of the section. Now you can find out D from this diagram, or if I go back again with this diagram, this is clearer. D is the distance from the center of the bar to the top. Now if I have the H, overall height of the section, from overall height of the section, if I subtract this cover, I will reach at the bottom of this stirrup. Okay, then I have to subtract this stirrup as well, the diameter of a stirrup, to reach at the bottom of the reinforcement. But this depth is from the center of the reinforcement, so it means that I will have to subtract half of the diameter of the main bar. So in that way, D will be equal to H minus cover minus diameter of this shear link minus half of the diameter of this bar. That's how the formula works. So H minus cover minus diameter of the shear link minus half of the diameter of the bar. So that's how we work out D.
Is there no space between the bar and the shear link?
There is no space between bar and the shear link. Bars are resting on shear link.
Okay.
Yeah. Don't just try to remember this formula. Simply see that how does it work. So D is from the center of the bar to the top of the beam. To reach at the center, if I have the overall height H, so from H I can subtract cover, then I can subtract diameter of shear link, then I can subtract half of the diameter of the bar. So this is how we got this formula. The applied moment MED is to be resisted by a couple between opposing forces, so T and CC. Now the lever arm Z is the distance between CC and T. Now Z will be from one force to the center of the other force. So this is lever arm. So this force CC is acting at half of the distance of 0.8x. It means that from D, if I subtract 0.4, then I can get a lever arm, can't I? Because this force is acting at half of 0.8, which is 0.4x. So that's the reason that we have Z is equal to D minus 0.4x, because 0.8 divided by 2 is 0.4x. If we replace this x with 0.45D, then Z is going to be 0.82D. This is where we get Z from. Now, if the beam does not have compressive steel or compression steel, it is known as singly reinforced beam. So if it doesn't have compression steel, in our case, we're not considering any compression steel, the maximum ultimate moment of the beam is given by MU is equal to CC into Z. So ultimate moment resisted by beam is CC times Z, is a force times lever arm or perpendicular distance. Now perpendicular distance is Z, which we found out 0.82. So simply put it here. CC we found out little earlier, which is here. This is C or CC. So 0.57 FCK into B into 0.8x, where x is 0.45D. And Z is equal to 0.82D. So let us see 0.567 times 0.8.
Sorry, sir. Can you explain why that part is CC?
The force in compression is resisted by Cc, which is force in concrete, and force in compressive steel. But here we don't have compressive steel. We will ignore this compressive steel, all right?
Yeah.
I did not write Cc, I just write C.
Oh, right. I see. So we're using the C from before. It's because
Yes.
we had that as C and not CC. That's what I was confused.
Yeah.
Thank you.
I'm a bit confused why you're timesing it by Z. Why Z is 0.45D times 0.82D, because before we said it was just 0.82D.
Yeah. Now what we have done over here is replaced this x. Okay, it's 0.567 FCKB into 0.8 times x. We have replaced this x with its value. X is equal to 45D. So we have replaced this x with its value. All right. So that's where 0.45D comes from.
Okay, I get it. Can you just go back to the last page again quickly?
Yes.
Okay, yeah, I get it. All right, thank you.
So we have replaced this x because for ductile failure, x should be equal to 0.45D.
So what's the difference between CC and C?
Yeah, I mean, here I simply wrote it as C because I was not assuming the behavior of the compressive steel. So here I'm assuming that compressive steel is not there. Compressive steel is not there, then say you can call it as C. Now here, just to distinguish it, the compression is taken by concrete and the bars in concrete as well. We will talk about bars in concrete when we will talk about doubly reinforced beams, okay?
Okay.
So CC is the force taken by concrete and T is force taken by reinforcement.
Okay, thank you.
Any more questions?
Just to clarify, by saying concrete block, you consider only one half of the entire cross section of the beam, right?
By saying concrete block, I simply take this stress block over here. I'm taking the area of concrete, which is up to this depth, 0.8 of x. So area of concrete up to 0.8 x will be this depth times the width of concrete beam.
Thank you, that makes sense.
Because this is a stress block. In a stress block, I have this FCD over here. I cannot simply multiply 0.8 x times FCD to get the area of the block. So for getting area of the block, imagine that only this portion, so there are no steel bars at the top. So imagine just this portion is contributing to concrete load, and this bit is equal to 0.8x, and the width is B. So B times 0.8x will give you area of this concrete. So the force which is resisted by concrete will be equal to the stress times this area. Does it make sense?
Yeah.
And the force which is resisted by bars is area of the bar. If there are 4 bars, then times 4 bars. So there may not be 4 bars times the stress in steel.
Would you redesign the bar size at the bottom or even top?
For singly reinforced concrete beams, we only design the bottom bars. But if the beam is doubly reinforced, then we design the top ones. Now the question is that how do we decide if it is singly reinforced or doubly reinforced?
So is MUD, is MU the same as MRD, which is for concrete?
It is, yes.
Right.
MU or MRD is one and the same thing. So when you multiply these things, you get MRD 0.167 FCK BD square. Remember that this is the moment resistance of a singly reinforced beam. First of all, we find out the applied bending moment, MED. And you know how to find out applied bending moment, don't you? So if you have a simply supported beam, you say if it is called UDL, W, if this is L, then MED is equal to WL square over 8 for uniformly distributed load. So if MED, applied moment, if it is less than MRD or MU of singly reinforced concrete beam, we can say that the beam is going to be fine, isn't it?
Yeah.
Now remember, here is the key thing. So if applied moment is less than the moment resistance of a singly reinforced beam, it means that we can design a beam as singly reinforced beams. It means that the compression reinforcement is not required. Yes or no?
Yes.
Yes. If applied moment is less than moment of resistance of a singly reinforced concrete beam, it means that this beam can be designed as singly reinforced concrete beam, and it will be safe. It means that no compression steel is required. But if applied moment is greater than MRD of a singly reinforced concrete beam, then you design it as doubly reinforced concrete beam. Then you add compression bars. Now here you would say that why don't we change the width of the beam? Sometimes because of architectural conditions, we are limited in terms of increasing the width or depth of the beam.
What is the limitation of just increasing your tension rods?
What is the limitation to increasing the tension?
Yeah, just so your steel bars that are in tension, couldn't you just make those a higher diameter, make the area bigger?
You can make the diameter bigger. It has to be balanced by the compressive side. If the tension force is really high, if the compression is really low, then what do? It's not going to be balanced, isn't it? So if tensile bars are too high, then it's not going to be balanced by the compressive force. These two need to be balanced.
What do you mean by balanced?
Means that the force in tension and force in compression, they have to be equal for it to be in equilibrium. All right.
Okay.
Singly reinforced beams, we simply work out the moment capacity of beams without compression steel can be determined by taking moments about concrete compression. So again, mu can be determined as T times Z or C times Z. So earlier we found out C times Z, we found out this mu, and then now we are saying T times Z, where T is equal to 0.87 Fy into AS. All right, we found out T a little bit earlier. From this T, we can find out area of steel. And then the formula for Z, again, it will involve a quadratic equation. And then from the result of quadratic equation is that Z comes out to be this value, where K naught is equal to MED over FCK BD square. First, we worked out moment resistance due to compression. Now we worked out moment resistance due to tension. For the time being, we are assuming that the area of tensile steel needed to resist the applied moment, MED, we are replacing this MU with MED so that we can work out area of steel. These are the formula where the ultimate resistance MRD of the beam that was using the concrete properties only. If applied moment is less than this, then you design it as singly reinforced beam. And if applied moment is greater than this MRD, then you design it as a doubly reinforced beam. It means that now you will require compression steel for it to be
in moment equilibrium.
These are the same formula as I talked about earlier. Let's go to this example.
Click on this side of the screen to watch this example and other worked examples on singly reinforced concrete beams. If you like this video, then consider subscribing to reach out to more structural engineers and civil engineers and students.